Here we're looking at the function f of x equals 1 over x minus 2. It has a horizontal asymptote of y equals 0 and a vertical asymptote of x equals 2. First thing we're going to investigate is the limit as x approaches infinity of f of x. So all we have to do is look at the y value that it's approaching as we go towards infinity, as the x values get very, very large, and it's approaching our horizontal asymptote of 0. The same thing happens as we go towards negative infinity. We're still approaching that horizontal asymptote of 0. So both of those limits are 0. As we approach 2 from the left-hand side, our function is decreasing without bound. It never hits 2 because that's where we have a vertical asymptote, but it's going down towards negative infinity. And as we approach 2 from the right-hand side, we are going up towards positive infinity. We are increasing without bound. An important point to note here is that a limit that equals negative infinity or infinity technically doesn't exist because a limit has to be a finite number. The next important thing that we can gather from this is that if the limit as x approaches infinity of f of x equals c, that means that our function has a horizontal asymptote of y equals c to the right. And if as x approaches negative infinity, the limit is c, we have a horizontal asymptote to the left of y equals c. And if both of these c values are the same, it means that it has a horizontal asymptote in both directions, that is y equals c. For some functions, the horizontal asymptote to the right and to the left will be different, and in some other cases, the function might have a horizontal asymptote in one direction but not in the other. For rational functions, a polynomial divided by another polynomial, if it has a horizontal asymptote in one direction, it has the same horizontal asymptote in the other direction. So we really only need to find one for rational functions. The way we can do this is by looking at our limit as x approaches infinity of f of x, and we'll note that this is infinity over infinity. So using L'Hopital's rule, which on the AP test you'll always indicate you are using, you'll take the derivative of the top and the derivative of the bottom to get 4x over 6x, which is still infinity over infinity. So using L'Hopital's rule again, you'll get the limit as x approaches infinity of 4/6, which is 4/6 or 2/3. And we'll say that this has a horizontal asymptote of y equals 2/3 in both directions. Technically, we only found one direction using infinity, but since we know it's a rational function, we know that it'll be in both directions. If this was on the AP test, you'd want to show both directions. You'd want to show the limit as you approach infinity and the limit as you approach negative infinity. For the second one, we'll do the same process. We'll look for the limit as x approaches infinity of f of x, and we'll note that it's infinity over infinity. So we'll apply L'Hopital's rule, and we'll look then at the limit as x approaches infinity of 4x over 12x cubed plus 1. And that's still infinity over infinity. So using L'Hopital's rule again, we'll look at the limit as x approaches infinity of 4 over 36x squared, which is now 4 over infinity, and 4 over infinity is 0, which tells us that this has a horizontal asymptote of y equals 0 to the right, and since it's a rational function, it's also to the left. It's in both directions. For the last one, when we look at the limit as x approaches infinity of f of x, we still get infinity over infinity. So we'll do the limit as x approaches infinity of 6x squared over 6x plus 1, which is still infinity over infinity. And then we'll get the limit as x approaches infinity using L'Hopital's rule again of 12x over 6, which is infinity over 6, which is infinity, which tells us that this does not have a horizontal asymptote in either direction.